So first, Professor Didier Henrion from the University of Toulouse will continue his talk from yesterday, keeping his promise that he will show some numerical computations in MATLAB and more practical matters. So Professor Didier, the stage is yours.
Thank you. Welcome, everybody. Indeed, this is the second part of my address for this Wombat conference. Yesterday, I introduced the moment sum of squares hierarchy for polynomial optimization. And today, I'll dig into more practical matters of the hierarchy. And indeed, I will run a certain number of small MATLAB demos. I'll post the scripts, the MATLAB scripts, in the Slack chat, the Slack environment attached to this conference, and as well as the slides, and probably also some lecture notes that I will be using partly. And then for this second part, I will not assume that everybody followed the first part. So I'll just summarize at the beginning what we saw yesterday. And then I will get into the technical details of constructing this moment sum of squares hierarchy. And hopefully it will give you a flavor of what's going on inside in the mathematics, but also in the computer programs. So what we saw yesterday was the following. So we started with a polynomial optimization problem, non-linear, non-convex, global optimization problem with possibly several minimizers, several global minimizers. So this was the notation. Yesterday, we minimized the polynomial P of a vector of indeterminates, X. And X, small x, the vector X of Rn belongs to a capital X set, which was assumed to be bounded basic semi-algebraic. So it's described as the intersection of finitely many polynomial superlevel sets. So the P1 to Pm, finitely many are multivariate polynomials of X as well, just as P. And capital X was assumed to be bounded so that there is no issue with the minimum being achieved. And we saw that this problem can be reformulated as a linear problem if instead of considering X as a variable, we consider a probability measure supported on the set capital X as decision variable. If we do that, we can also use Lagrangian duality to derive a dual to this problem on measures, which will be a problem on continuous functions, which are non-negative. And we interpreted this dual as the problem of finding the largest lower bound on the graph of P on capital X. And then, since we assume that the data is polynomial, P is polynomial, instead of manipulating measures and continuous functions, we manipulated actions of the measure on a certain number of test functions or basis elements of the vector space of polynomials of degree up to d in n variable, and these we call moments. And so we come up with a primal dual formulation, which is in terms of moments and positive polynomials. And we argued that these constraints of being a moment vector or being a positive polynomial on capital X are difficult constraints. And for that, we replace these conditions of positivity by easier conditions, namely moment relaxations, semi-definite moment relaxations in the primal. I denoted this like that. and sum of squares strengthenings or reinforcement in the dual. So introduce this cone here of weighted sum of squares and its dual, the cone of pseudo moments, moment relaxations. This constraint here was just to model the fact that we are seeking a probability measure, so the 0th order moment or the mass of the measure should be 1. These constraints here are outer approximations of the cone of moments in the primal and inner approximations of the cone of positive polynomials in the dual. And hence the values that we get here are indexed by a certain integer denoted R, which somehow measures the accuracy of the approximations of the, on the one hand, moments, and the other hand, positive polynomials. Since here we are optimizing over a cone which is in general larger than the cone of moments, and we are minimizing, the value here obtained by solving this problem is in general less than the value of the original polynomial optimization problem. And that's also true for the dual. There is strong duality between these two problems. And however, when R increases, the quality of the moment relaxation or sum of squares reinforcement increases in a way that we produce a monotonically non-decreasing sequence of lower bounds on the global minimum, and thanks to results of real algebraic geometry, namely positive shell and Z-cell representations of positive polynomials, we could prove convergence of the hierarchy. So that was yesterday. So we replaced a difficult nonlinear non-convex problem by a family or a hierarchy of easier problem, namely semi-definite programming problems. So linear optimization problems in the cone of non-negative quadratic forms. And these semi-definite problems, they are in the family in the sense that they get better and better lower bounds on the value at the price of having a feasibility set here in the primal and in the dual, which is larger and larger. So the bigger the R, the more computationally challenging is to solve this primal dual semi-definite program. So what I would like to do in this second lecture is to explain how this cone here approximation are constructed very explicitly, and how the dual is constructed. And I will then show you an example or two of explicit constructions of the moment relaxation linear matrix inequalities, this semi-definite problem here, so that you have an idea of what it looks like in practice. Once this is done, I will show you on MATLAB a few examples of constructions of these LMI relaxations and their numerical solving. So that's the plan for the beginning. So first I will, as I said, show that finding whether a polynomial is sum of squares reduces to semi-definite programming. Then I will construct these moment LMI relaxations, as I said. And when it goes to, during the demo, I will show you results on the rank of the moment matrices that I would have constructed by then, and how this detecting the rank pattern of these moment matrices can be used to detect global optimality and finite convergence of the hierarchy. So let me get to the previous slide. Here, there is this asymptotic convergence in theory, but in practice, we observe that the convergence is finite, actually generically is finite, as we discussed yesterday, which means that for a finite value of R, P star R is equal to P star, or equivalently, solving the original non-convex polynomial optimization problem amounts to solving a finite dimensional SDP problem, semi-definite problem. And to know whether solving a finite dimensional SDP problem is actually equivalent to solving the original problem, we'll use this rank pattern condition. So I will show you how this works in practice. And then, if time allows, I will show you a little bit more about retrieving the global minimizers. And especially in the case we don't have finitely many minimizers, how the so-called Christoffel-Darboux polynomial can be used to approximately get the support of the measure supported on a variety of global optimizers. And maybe also during the session, depending on your interest, we may address other questions. So as I said yesterday, don't hesitate to take the floor, to activate your mic and to ask a question if you feel the need for it. I don't mind being interrupted, quite the opposite. It gives some, at least it gives me the impression that somebody is following. Since we are not in a real situation of a real conference, it's always a little bit strange to talk alone. So don't hesitate to interrupt and to interact with me.
Okay, Didier, so I'm interrupting now. I have a general question.
Yes.
Does it generally make sense to apply this framework to equality constraint problems when you only have equalities?
Yes, yes. I will show an example with equations, actually. Yes, you can have equalities here. It does not make any difference. Okay, formally, I did not put equations here because I was just lazy, and notationally it's more busy. But think of if you have P1 equals 0, just take P1 bigger than 0 and minus P1 bigger than 0. This does the job. But more concretely, if you have an equation there, the formulation is simplifies somewhere in the relaxation, and we'll see that later on. So without, yeah, there is no problem to have equations.
Okay.
I also have one very silly question. Does that make sense to consider X as a binary variable?
Oh, absolutely. So if you have, for example, P1, which is equal to 1 minus x squared and P2 minus 1 plus x squared, then you have that x is plus minus 1. We'll see an example, a very simple example of a binary problem, the three-dimensional max cut problem that I will be using just to illustrate how the moment relaxations are constructed. Yes, binary problems are covered by this framework indeed.
Thank you.
Yes. Other questions at this stage? So yeah, okay, of course the survey of yesterday's talk was fast, especially if you did not follow yesterday's talk. It could be a little bit hard for you to catch up. But I think I said it all. So don't hesitate if you did not see the lecture of yesterday and you have questions, you have chance now to catch up a little bit better. Questions?
Yeah, we have one comment in the chat as well. But
yeah, can you read it, please? Because I don't want to toggle screen sharing.
It's a comment from Evgeny. Sorry, I couldn't pronounce your name correctly. Is it the act sufficient to add just one inequality to get equalities? Yeah.
Well, no. If you actually, I said I was lazy to deal with explicit equations. We could have equations, and the equations actually we don't deal with them as two inequalities with separate signs.
Sorry,
we really deal with. Yes, that's the question.
Evgeny was talking about the binary constraints.
Ah, okay.
You need one inequality.
Yes. Okay. No, but there may be more. Of course, there may be as many as the number of variables. And actually, if you have binary constraints, then you have a lot of structure that you can exploit so that the moment relaxation, then they can be simplified somehow. There are a lot of variables that are redundant that you can remove, and yeah. So an expert in that, if you're interested, is Monique Laurent from Amsterdam. She has been doing that very actively during the last 20 years to exploit binary constraints in the moment sum of squared hierarchy. So I welcome you to look at our work on the topic. Monique Laurent from Amsterdam. Other questions? Yes, so in terms of the platform, the computer platform I'll be using, it's MATLAB. Just because it's convenient for me, it's well, I have an engineering background, control engineering background, so I've been using MATLAB for years. Of course, MATLAB deals easily with matrices. You'll see we manipulate matrices easily. Will be for solving semi-definite programs, semi-definite optimization problem. You will be using Sedumi, just because it's very simple to use within MATLAB. But right now there are more efficient implementation of the algorithm of Sedumi in the Mosaic package. The semi-definite module of the Mosaic package is the one we usually use now. It's as good as Sedumi, but better engineered, faster. To our experience, at least. And there are other SDP solvers that you may want to check. There are many publicly available softwares. To construct the LMI relaxations, we'll be using our interface Globtipoly that was designed in 2002 by Jean-Bernard Lasserre and myself. And so the Globtipoly is an interface within MATLAB that allows you from the polynomial here defining the problems from P1, PM to construct these semi-definite problems here. So it will construct actually this one, the moment problem, the moment relaxation, linear matrix inequality. So it does that for you. You don't have to do it from scratch. I will show you right now on the paper how this is constructed, but you don't have to care about the details anymore after you understood how it is done, because Globtipoly does that for you. Okay, so now the plan is to show you with just pen and paper how testing whether a polynomial is actually semi-definite programming, and how the matrix LMI relaxations, the moment matrix LMI relaxations are constructed. So now I will share, I will use a little camera, which is here in front of me. Hopefully my handwriting will be readable. So you remember this cone that I introduced yesterday, this sigma of XR. It was defined as a cone of polynomials of degree D, such that they can be written as a sum of weighted polynomials pk, and I said that the sk are sum of squares, and I also mentioned that the degree here of this term, each term here under the sum is less than r. So these pk's, they define the set x over which we optimize. Just like that, and I assume that one of the P1, the pk's here, maybe the first one is the equation of a ball. Without loss of generality, since the set is bounded, we can choose one of them like that for R sufficiently large. I assume also that for notational convenience that P0 is just the constant polynomial equal to 1. And so that the sum here ranges from 0 to m. And these weights, they are polynomial sum of squares. So polynomial sum of squares denoted sigma. So sigma, it's the cone of polynomial sums of squares. So as the name says, it's just all the polynomials that can be written as sums of squares of other polynomials. And now I will show you that testing whether polynomial belongs to this cone actually boils down or reduces to semi-definite programming problem. So remember in particular that also this cone, it is called actually a truncated quadratic module. If you're interested in knowing more about these objects. And of course, we argued yesterday that it is a subset of the cone of polynomials that are positive on capital X. I will not explain that any further, refer to yesterday's lecture. This is an inner approximation of the cone of positive polynomials on capital X. So now to the claim that testing whether sigma, whether a polynomial is in sigma boils down to semi-definite programming problem, to semi-definite optimization. Then I do, for that, I will use just a basis to represent my polynomial. So yesterday I denoted B. So it will be a basis of a polynomial. So it's B, a vector of polynomial. Since I have polynomials of degree D, it's a finite dimensional vector space, polynomial of degree D in n variables. So I take a basis for this vector space. I indexed it by a vector of integers. I denoted it like that yesterday. So it vector integer indices summing up to D or less. And then P, a polynomial belongs to sigma if and only if I just say that P can be written as the sum of squares of other polynomials. This is for some Qi, just polynomial, and hence they can be written, this polynomial, they are functions of x, they can be written in this basis as a linear combination of basis elements. So let me denote it like that by a vector scalar product. So this is a row vector of coefficients, this with transpose. So Qi without the transpose is column vector of coefficients of polynomial, and B is the vector, the column vector of basis elements. This is just a way to write a polynomial as a sum of basis elements. Okay, so that this sum here can be rewritten like that. So let me now denote explicitly dependence on x. This sum here can be written just by plugging the expression of Qi, of the polynomial Qi, like that. And hence, I can also rewrite it like that by rearranging the terms. And then I can put the summations, the summation inside, like that. So that here I have a row vector, here I have a matrix, a square matrix, and here I have a column vector. So this matrix here, I denote it Q, and this matrix is a sum of, okay, there is a transpose here, a sum of outer products of column vectors. So it's a sum of rank 1 positive semi-definite matrices. So this matrix is positive semi-definite. So you see, as soon as P is the sum of squares, it can be written as a quadratic form in the basis vector, the polynomial basis vector, and the matrix of this quadratic form is this Q matrix. Now, this is called a gram matrix. So now if P is given and you want to know whether there is a Q matrix allowing to write P as a sum of squares, you see that there is a linear relation between entries of Q and coefficients of P. The relation is just obtained by identifying like powers of X on both sides of this equation here. And you see that the relation between P, the coefficients of P, and the coefficients of this quadratic form, Q, is linear. And hence that finding whether P belongs to sigma boils down to finding a PSD matrix Q linearly related to P. So that's exactly what semi-definite programming is about. Clear enough?
Sounds great to me.
Yes? Questions? Okay, so now to the second part. Oh, by the way, yeah, sorry, I did not mention, but that was for sigma. But since sigma capital X R can just be expressed linearly as a convex combination of elements of sigma, then of course sigma X of R also has an explicit semi-definite representation. It's just a projection of the semi-definite code. Okay.
Question?
Yes.
Russell and Göttingen. So I guess two questions. The first one is your goal is to decide whether or not your polynomial P is in this set, right? So a yes, no
yes.
Query, right?
Yes, yes, yeah.
So numerically, you would test that by watching something blow up to infinity, or what would be the general numerical philosophy to verifying that?
Yeah, okay. So if you want to know whether P is a sum of squares, then you have to know whether P expressed in some basis, so here B, can be written like that, as a quadratic form in a basis B. And the matrix of this quadratic form is denoted Q. So you want to know whether there is such a matrix. So P is given, Q is unknown. You see that the relation between Q and the Q matrix and the P polynomial is linear. And so you have to find whether a particular linear slice of the cone of positive semi-definite matrices is empty or not. That's the semi-definite feasibility problem, if you want.
Correct. So I have some experience in this in inverse scattering, and the way they decide whether something is in the range of some operator is by taking the inverse and trying to solve the equation and seeing if things blow up to infinity. So how would you do this?
No, we would not do that. What we do is that there is a linear map that links Q, capital Q, to P. So this linear map are denoted A. It's a linear operator from the space of symmetric matrices of size capital N, say, let me denote it like that, symmetric matrices with real entries, which are square and of size capital N, to the coefficients of P. So this is a vector space, and its dimension is this binomial coefficient. So this A of Q should be equal to P, sorry, not B, P, where P is the vector of coefficient corresponding to my polynomial P. And so you want to know whether there is a matrix Q such that, which is positive semi-definite, such that the image of this matrix through this linear operator, which is explicitly given, is actually P. So whether P is in the range of this linear map, that's exactly it, yes. And that's semi-definite programming. You don't have to minimize anything here.
Right, you're solving an equation that doesn't have a solution. So I guess my question again, it's not answered.
Yeah.
How do you numerically observe that P is not in the range of this A?
We use semi-definite programming. So we solve this. This is a semi-definite optimization problem where you don't minimize anything, but the feasibility constraint is given in that form. So we use a semi-definite solver, inter-point methods. Does it answer?
No. How do you know that? Okay, I can plug it into my SPT solver. What does my SPT solver tell me? Does it tell me something is infinite? Does it tell me that something
okay.
an answer?
So if you're using primal dual methods, either you have a matrix Q numerically computed, and you can check whether it's positive semi-definite just by checking the minors, and whether this is true up to numerical accuracy. You can check that a posteriori, or the primal dual algorithm returns a Farkas certificate that this system has no solution.
Okay,
and
so
this you can check as well using duality.
There doesn't exist a solution.
Yes, you have a certificate that it does not exist as well.
Okay, okay, thanks.
Yes?
Sorry, can I ask?
Please.
Reina here from Adelaide. Can I ask, it depends on the basis that you use?
So the basis here is just, well, the linear map here will depend on the basis, but that's all. Up to change of coordinates in the space of symmetric matrices, the system will be the same. But of course, with a different basis, the way you represent your linear operator and the way you represent your polynomial P will differ. But the problem will still be always finding whether the cone of positive semi-definite matrices, this non-polyhedral cone, has an intersection with a given subspace. And the subspace will be given by this linear map and this polynomial.
That's fine. That's fine.
You want to know whether there is a point here somewhere.
I think, can I ask a question as well?
Yes.
So I think that's actually related to the paper that you said to me, but I think this feasibility problem cannot be strong, weakly infeasible or something like that.
So weakly infeasible.
Because
yes, it can.
Because it can be weakly infeasible.
Yes.
Okay. So I think that has something to do with what Russell was asking. So if this problem is not weakly infeasible, then you can detect this numerically in a quite robust manner.
Absolutely.
But if it's weakly infeasible, I think you might have some trouble.
Okay. Absolutely. If the problem is weakly infeasible, then you still can have a guarantee, a certificate of weak infeasibility, but it's much more computationally intensive. Actually, to find the certificate of infeasibility for semi-definite programming, you would have to use the moment sum of squares hierarchy itself. So this is the work by, there is a very nice work on that by Igor Klepp and Markus Schweighofer.
So so I think that is the real algebraic geometry point of view. So
yes,
so people from the SDB side, sometimes they use this facial reduction stuff.
Yes, that's an alternative to that indeed. That's not the only way, of course, but that's one way. But there may be others, indeed, reductions, facial reductions. Yes. Yep.
Thank you.
Okay. So that was for the sum of squares side. Now for the moment side, I will construct explicitly the dual. So the dual to the quadratic module, the topological dual, is the set of linear functionals that are non-negative on the primal. So since we are a cone, so it's linear functionals that will be parameterized by a vector y, and there will be a linear function that I call the Riesz functional, and it should be non-negative for all elements, for all polynomials in the truncated quadratic module. That's by definition the dual. So this Riesz functional, it takes a polynomial and returns a real number. So it takes a polynomial p of x and returns actually, if you express this in the basis b, it will return the inner product of p and y for a given vector y. So once this is, well, that's the definition. We can reformulate that as follows, just by taking the definition of elements in the primal cone here. And this is for all sum of squares of bounded degree. But since this is for all sum of squares, this is also true pointways in K. So for each index K, since we have here a linear functional, it's true that it's the same to say that each of the element in the sum is non-negative for a single square, not for a sum of squares. This is a convex cone, this is a linear condition. So it would be for sum of squares, but it's also true for a single square, and it's also true for all K. So that we have this reformulation. And the degree here should be also less than R. So once this is done, we look at this condition here. Okay, and this should be true for all K. We looked at this condition here, and we expressed it as a quadratic form in Q. So we see that we have a quadratic form. So we take a polynomial and return a real number. So the polynomial is Q, and return the value of the Riesz functional at the product of pk and q square. So that's a quadratic form in the space of polynomials q. And this quadratic form, so quadratic form, is actually a matrix. It has a matrix representation in some basis. And this matrix, we call it the localizing matrix. So it's a localizing matrix. And we denote it like that. M d of p k y, and we do that for each value of k. Okay, so it's a symmetric matrix. It's a quadratic form, and so pk is fixed. And as a function of y, this matrix is linear, just because the Riesz functional is linear as a function of y. So it's a symmetric matrix which is linear in y. And since this must be non-negative for all q, it is the same as saying that this matrix is positive semi-definite. So that this cone is actually the same as the cone of all matrices being So here I have the degree. So D is the degree of, actually is the degree of Q. So here we have a certain, well, it depends on the degree of PK. So we should be a little bit careful. Let me call it like that. Since the degree depends on the product here. And this is, this must be PSD for all K. So if we have finitely many matrix inequalities which are symmetric and linear in Y, this is why we call that an LMI, a linear matrix inequality. When K equals 0, this localizing matrix, it's called a moment matrix. So that's an explicit description of the dual cone. Another way to think about it is just to write MD, this localizing matrix, as the action of the Riesz functional on the entries of rank 1 polynomial matrix, which would be this one, where B is the vector, the column vector of basis, as we introduced before. So here we just, this is a symmetric matrix, which is polynomial and rank 1, positive semi-definite. We let the Riesz functional act on it entry-wise, and we have this localizing matrix. Okay, so all of that is, let's say, maybe a little bit too abstract for some of you. So let me show you now the explicit construction in a given example of polynomial optimization of these constraints in a monomial basis. So we use B, the basis of monomials, so that all these manipulations are much easier to see. So for that, I use lecture notes that I prepared for engineering graduate students some years ago. And okay, so I put a reference in the on the Slack. So that's a linear matrix inequality optimization for control. And so in the section 3, there is this explicit construction of the LMIs, and let me show you how they look like in a given example. So here I explain again what I just mentioned about the moment matrices, and the Riesz functional is defined here. So that's a given example of a bivariate polynomial, so that we can see that the action of the Riesz functional here is just the action of linearizing the polynomial. So the vector here, y, is indexed by this A vector of integers, which are actually powers of the indeterminates here in the monomial basis. You see x1 squared corresponds to y2, 0, x1, x2 is y11, and so on. So that the moment matrix actually is this quasi-Hankel form. So if you just do the computations, you observe that the moment matrix look like that. And you see that there is this embedding property, so that the upper left corner of the bigger moment matrix is actually the smaller moment matrix. They are embedded within each other. Just because polynomial of higher degree includes polynomial also of lower degree. You see, and you construct these matrices here for increasing value of the degree of the moments here. You see here you have moments of degree up to 2, here of degree up to 4, and so on. And that's for the moment matrix. For the localizing matrix, it is the same, but you just have shifted version of the moment matrices and linear combination of them, depending on the polynomial with respect to which you localize the moment matrix. Okay, so all of that is very explicit. And you can see on an example, maybe this one, this is the polynomial optimization problem. in two variables, very simple. This would be the first LMI relaxation. This is a constraint that the probability measure, the measure must be a probability measure. This is the moment matrix constraint, moments of degree 0, degree 1, and degree 2 here in the bottom right corner. And these are localizing matrices here, just scalar constraints corresponding to these three inequalities. So that's the first LMI in the relaxation. So R is equal to 1 in my notation. And then the second one is just bigger. You just inflate the degree, and so you have more moments, you see, of degree up to 4, and then you localize with shifted moment matrices the constraints as well. So now to answer the question on equations, so if instead here I would have an equation, maybe this one would be just an equation, 1 plus x1, x2 equals 0, then it translates directly into an equation here in the moment space. You would have equal 0 for the first relaxation, and here for the second relaxation, you would have all these matrices identically equal to 0. So it's just a collection of additional linear constraints on the moment. So here on this example, we observe that if we solve this semi-definite problem, this first LMI relaxation, we get a lower bound on P star, which is equal to -2, and which is strictly less than P star. If we solve the second LMI relaxation on the computer, we get a value P2 star, which is bigger than P1 star, and which is actually the value of P star, which is this number. And so that here the first LMI in the hierarchy was just a relaxation, and the second LMI does the job of solving the problem globally. Now, how do we know that actually P star is equal to P2 star in this example? Well, we have a general strategy which is based on the rank condition of the moment matrices, which says basically that if I solve my LMI relaxation at a given relaxation order, and if I denote Y star the solution in the moment space, if the rank of the moment matrix does not increase when I look at these embedded matrices, you may remember this moment matrix here, it's a moment matrix of degree up to 4, but it contains in its upper left block, 3 by 3 upper left block, a moment matrix of degree equal to 2. So they are embedded within each other. They have this quasi-Henkel structure. So if the rank of this 6 by 6 matrix is equal to the rank of the 3 by 3 matrix, then that's a certificate that solving the LMI actually is equivalent to solving the original problem. In particular, this would be the case if this whole matrix is as rank 1, because then all the sub-matrices will have rank 1 as well. Okay, so that the certificate of finite convergence, this is called the flat extension property. In particular, it's true if the rank is 1. So this is the way we test global optimality of the relaxation. Questions on that?
Russell again.
Yep.
And you can get this actually numerically exact because the rank only increases by integer amounts. Is that correct?
Well, numerically, we cannot really compute the rank, because what we'll do is to use singular harmonic decomposition, which is done with floating point arithmetic. So we just test drop of singular values. We don't have an exact rank condition in the sense that we do not manipulate rational we manipulate on the computer only rational numbers, but the solutions of the LMI problem in general, they are algebraic numbers. For example, the value here of this problem is not a rational number. So originally, this test is not done exactly. Is that
good? Yeah. I'm just wondering. I mean, still, could you from the jump in the singular values, could you still come up with a? I'm really wondering about mathematical statement you could make based on your observation of the numerical computation. So I mean, the numerical computation is an experiment, right? And then what do you say about that experiment?
Well, the mathematical statement is this one. This is purely mathematical. But then numerically speaking, evaluating the rank of a matrix is tricky.
Yeah. Okay.
Yeah. This is really the rank, the number of non-zero eigenvalues. So these matrices are positive semi-definite. Okay, let me show you now. Let me show you how it works in practice with MATLAB for a simple example or two. Where is it? Yeah. Okay, hopefully you can see my MATLAB window.
Yes, we do.
Good.
But do you want to show also your face on camera?
Ah, yes. Let me check that. Yeah, yeah. Yeah, I have to get back to this to change my camera. Yep. That's me. And let me get back to MATLAB. Yeah, here you are. Okay, so let me solve a very simple problem first, and then a little bit more complicated. That's a problem of minimizing a polynomial, which will be just in one variable. So that's a global poly command to declare a variable, a scalar variable. I will attach a measure to this variable that I will denote mu. And I define my polynomial. Let's say that I choose this one, x squared minus 1 squared. Oops. Okay, so that it's a degree 4 polynomial. And of course, if I minimize it, I should get two global minimizers, plus and minus 1. Okay, so the way we input this in global poly is the following. So I construct the moment semi-definite relaxation of the problem of minimizing P. By default, it will construct the smallest of all relaxations. So since P is degree 4, there will be moments of degree up to 4. And you see there will be only 5 moments. That's a very simple problem. And there will be linked with a moment matrix, which will be a Henkel matrix of size 3 by 3. So if you want to see the semi-definite problem corresponding to that in Sedumi format, you can use this command. So if you are familiar with the input format of Sedumi, this creates a semi-definite program in ABCK format, and the moment relaxation is in the Sedumi dual format. So it will be the Y vector. So if you're not familiar with Sedumi, forget about that. But then once this is done, you can solve the problem by calling this global poly command, which will call Sedumi to solve the LMI problem, the semi-definite problem. So it calls the solver, here Sedumi, could be another one, but here you Sedumi. It solves the problem, and you see that it does this test of the ranks of the moment matrices and concludes that numerically the rank stabilizes to 2. Then it does some additional checkings and actually concludes that there are 2 solutions which can be extracted with a double command, which is indeed corresponding to what we expect. Now, if you want to have access to the moment matrix, there is a command to do that. So mmat mu construct the moment matrix symbolically and double extracts the value obtained by the solver, and it stores it in a matrix, which is a 3 by 3 matrix. And you can check that indeed this matrix has rank equal to 2, and that its upper left block of size 2 by 2 is the identity matrix, so it has rank 2. Okay, so this matrix actually is the sum of 2 rank 1 matrices. Each rank 1 matrix corresponds to a global minimizer. So there is a global minimizer at +1, and there is another which is at -1. So you can just construct this like that. So you take the monomial basis evaluated at +1, and you take the outer product, and you do the same for the monomial basis evaluated at -1 and take its outer product with itself. Okay, so this is 1x and x squared evaluated at these points. And of course, if you do that, you should divide by 2. This must be a probability measure, so it will be a convex combination of 2 rank 1 matrices, but with the weights summing up to 1. So you get indeed that this corresponds to this moment matrix up to numerical accuracy, of course. Okay, now you can do a little bit more complicated problems. Of course, this is a very elementary problem, but let's say that we want to minimize a polynomial, random polynomial on the sphere. So let me take this script here and 10 variables. And you see here, I construct actually B is the basis of monomials of degree up to 4. P is a random polynomial of degree 4 in these 10 variables. And here I construct the problem of minimizing this polynomial subject to the constraint that X is on the unit sphere of dimension 10. Of course, now the problem is a little bit harder to code. Whoops, sorry. That's what happens usually when you do a demo. So let me just clear everything and do the stuff again. Okay, so you see that there are 10 variables with 4, and now there are 1,000 moments in my relaxation. You can have a look at the size of the semi-definite problem. You see, you have a semi-definite cone of size 66 by 66, and there are 66 linear relations corresponding to the localizing matrix attached to the sphere constraint here, these equations. And then we can solve this problem. Okay, maybe you want to know to see the monomial basis here. B is a vector of monomials. You see there are many of them. There are 1,001 monomials of 10 variables of degree up to 4. You can see all of them here. And then I can solve the LMI relaxation, calling Sejumi. And you see here that I obtained rather quickly rank 1 moment matrix, actually, corresponding to the global solution. So that's the global solution, the one that minimizes my polynomial. So the polynomial was random. Okay, it can't be seen. It's a very messy polynomial with many variables. But if you look at the value taken by the polynomial at that point, it should match with the value obtained by the LMI relaxation. And also, you may want to check that this is indeed on the unit sphere, and you can check that indeed it is a unit vector. Okay. So I think we can stop here. I will provide more demo scripts if you're interested. There is this Christoffel-Darboux polynomial that I did not have time to show, but I will provide references, and I'm ready to take questions on that part.
Yeah. So in the audience.
My apologies. I couldn't hear what you said.
Sorry. So I'm sorry. So in the audience, is there any questions for the speaker? So I have some questions first. First of all, I can see, I'm not sure or not, the dimension blow up significantly.
Yes.
And another thing is regarding the your previous talk, like in your proof, is actually X is not don't need to be Rn. It can be just any discrete set. That's why I asked the question that does that make sense to consider as a discrete set like binary variable? Mm-hmm. Because when you in your proof it doesn't really need what is X is. You also mentioned it, and Puno also asked about this. Mm-hmm. So what do you think? Because like discrete optimization people, they struggle with linearize the like objective function.
Yes.
And
okay.
So do you think that this makes sense?
Yeah. It has been studied a lot. This Moment-Samoskos hierarchy for combinatorial optimization. Mm-hmm. Okay, there is no miracle. You can prove that there is a finite dimensional SDP problem, which is equivalent to solving the original combinatorial optimization problem. But if you want to have guarantees that it always does the job, then the size of the resulting SDP problem, this moment LMR relaxation, is of course exponential as a function of number of variables of the original problem. There is no miracle.
Yeah, I can see that.
Yes, of course, yeah. Then the way the number of variables grow, yes, it's a polynomial function of R, the relaxation order, but the exponent of this polynomial is n, the number of variables. So viewed like that, it's exponential as a function of number of variables. But you are at solving a very broad class of non-convex, nonlinear problems. So
it's a trade-off.
There's no contradiction here.
Yeah. Okay. Thank you. Thank you for your answer. Is there any other questions from the audience?
I have a question.
Yeah, Vera. Yeah. And Russia as well. Sorry.
Didier, so in your view, what's the biggest challenge to these problems? Is it dimensionality or is it stability?
Both, actually. Yeah, that's true. Even for simple, small problems, we still don't understand everything. There are issues, okay, due to the choice of the monomial basis, but not only. Even if you use a basis which is tailored to your problem, you may still have problems with weak infeasibility, as we discussed, unboundedness, already for small dimensional problems on the one hand. So this is still not fully understood. On the other hand, if you want really to make things scale up, it's essential to exploit the problem structure. So symmetries, action of finite groups, leaving the problem invariant, sparsity patterns that can be exploited. All of that is subject of intensive research currently. And well, for example, we can solve rational optimization problem with thousands of variables routinely with these techniques as soon as the rational optimization problem has a lot of sparsity. So there are many terms in a polynomial, you have a sum of many terms, but each term depends only on a few number of variables. That's one way to exploit sparsity. So we can really make the hierarchy scale if we exploit the sparsity and the structure. And this is currently investigated a lot and also critical. Yes.
If I could follow up on that, if you had a quantum computer, would that change how you would solve these problems, or what problems you could solve, or would that open up new possibilities for you?
Yes, this I don't know. I know that people have been investigating that, but I can't really. I'm not well informed about the state of the art. No. Solving SDP with quantum computers, solving the hierarchy with quantum. I don't know. No.
Okay, thanks.
We have one more question from Vera, and then we will move on to the next speaker.
Yeah, just a quick question. So if I'm solving a problem for which I want an exact solution, in principle, I can solve it numerically, right? Then guess what the actual values are, and that will give me a certificate, right?
Yes. Okay, that's an interesting question indeed. So you saw that in general, even though all the coefficients of the semi-definite problem are integers, you cannot expect the solution to be a rational number. In general, it's not. It's an algebraic number, however. It's the coordinates of the solution are roots of univariate polynomials with integer coefficients. But these univariate polynomials, their degree, it's called the algebraic degree of semi-definite programming, they are huge. They are very big. There has been studies on that. And so the price to pay to solve an SDP problem exactly is really significant. So right now we have computer packages using critical point methods and drop-down basis methods to compute exactly solutions to SDP problems, but it's very limited in size. Say you can go up to 10 variables and cones of size maybe 10 by 10, not beyond. But there has been studies on that. I can give you a pointer to a software package called Spectra that we developed jointly with Mohab Safieldin in Paris and Simone Naldi from Limoges.
Yeah, thank you very much for this.
Okay, thank you. And then we have one more question. So, are your lectures notes available somewhere? Are your lecture notes available?
I will put them on the Slack. So everything that I shown during this talk and also a little bit more will be posted on the Slack environment so that you can have a look. Yes.
Okay, thank you. So thank you very much.
You're welcome. Thank you for your attention.